the derivative of e to the x was e to the x.
Yeah.
Dun, dun, dun. I know, but that's why I get to you, right? So it says, which of the following pairs of graphs could represent the graph of a function and its derivative? So everybody that said C, you're not wrong. Those graphs are each other's derivatives. So this goes back to kind of taking in that table, remember? So if the original is increasing, the derivative is positive. If the derivative is decreasing, then the derivative is negative. But do you see how that actually still applies here? The original is increasing, derivative is positive. The original is concave up, derivative has to increase. So it actually follows all of the rules. Well, it should, because it's actually the derivative. But you could have actually gotten it even though you didn't know what the derivative of e to the x was and that its derivative is e to the x. Yeah, you're just still all mad at it. LC.
I'm just happy Dom didn't get it right.
Oh my gosh. All right, well,
I can't wait to see
ta-da! The derivative of e to the x is e to the x. Such a big height.
I thought we've known this by now.
Then why didn't you get the question?
You're lucky this is recording, right?
But you know, it's calc. And life doesn't stay easy in calc for more than one example. Because x has a derivative of what?
1.
So you don't see the effect of the derivative of x on that function. However, if the derivative of e to the x is raised to something other than x, so we'll call it a function u, then the derivative gets manipulated a little bit. So now the derivative of e to the u is e to the u times du dx. But remember, du dx is the same as saying u prime. I want to know if when Spencer watches it, the board shakes on his end.
I don't think so.
My question is, is Spencer really going to watch it?
I love Spencer. Did you watch it? Did it shake?
I mean, you'll get
It comes back and
video.
answers the question. We'll know.
Because it's really, it's going off the computer screen.
Yeah, it won't shake.
That's what I said. Touche.
Thank you, Dom.
Dom.
All right, so e to the u times du dx. I thought you were going to. I said it doesn't stay easy forever, but the rule is kind of easy. Let's apply. We got x squared times e to the negative x. So this is a two-part problem, right? Because x squared is a function, e to the x is a function, therefore we need to use the product. Let's use a pretty new color. So it's dy dx equals the first, which is x squared, times derivative of the second. Anytime you have an e to something power, you literally rewrite it exactly as it is. So the second will be e to the negative x. Here's the trick. Got to multiply now by the derivative of its power. So the derivative of negative x is, so that's the only thing you got to add. So first times derivative of the second plus the second, which is e to the negative x, times derivative of the first. What's the derivative of x squared? What do we know about negative exponents? Hey, they're a no-no, right? So to get this as a final answer, we're going to drop the e to the x down to make it positive. Since both of them have an e to the x, we can make one common fraction. Right? Because you can drop that one down, so then you combine the numerators. So you have negative x squared plus 2x.
Could you do move the e to the x down and then take a quotient rule? Or,
Yeah, it would be
I mean, would it work?
messier. Because eventually, if you did it that way, to get this for a final answer, you'd have to factor out an e to the x and cancel one. So this had an e to the negative x, and that has an e to the negative x. So you're not allowed to have a negative exponent.
Right.
So both got dropped down. So when you drop them down, it was like negative x squared over e to the x plus 2x over e to the x. So since they had like bases, I could write it as one fraction. It'd be like 1/2 plus 3/2. If you can write it as 1. Okay? E to the tan of x. So the function that it's being raised to is tan x. What's the derivative of tangent?
Secant squared.
Good job.
Yes.
So the rule, if you go back to the rule page, is dy dx equals e to the u times u prime. So in the case of this problem, plugging in your u and u prime, you get e tan x times secant squared x. And that's your answer. Yes.
When you say like go back to the rule page and stuff, like that's literally just a chain rule, right? Like there's nothing special about it.
Yeah, it's a modification of the chain rule.
How?
Because the chain rule says take the derivative inside, then the outside. But like this isn't really like an inside-outside function. It's a modification because it's kind of like function composition, where like e is being composed with another function u.
Okay.
Do you know what I'm saying? Like,
Yeah, I think so. But like it's still because the derivative of the inside is just 1, so isn't it still the chain rule and you're just or 0? Actually no, never mind. I'm lying.
okay, I was like,
Yeah.
I'm so confused. So I was like, no. Now, if you don't like it written like this, you can rewrite secant squared x in front and write it as secant squared x e tan x. But that's seriously more of a preferential thing than it is an actual, like, you need to use. Okay? So Dom asked about doing the quotient rule. This is a case where you have a choice, but I would probably do the quotient. Like you could bring it up as a negative exponent, but then you're kind of playing with fire with all the negatives you have to add back into it. So this is a case where I would probably do the actual quotient rule. So again, it's been a while since I feel like I said hi ho, hi ho. So high on top, ho on bottom. So then it's ho d high. So it's the bottom times derivative of the top. What's the derivative of cosine?
Negative sign.
And then you have to remember that this one is a chain rule because that derivative of the outside is negative sine, but the derivative of 2x is 2. So ho d high minus high d ho. So it's always e to the 3x times derivative of the exponent, which is 3, all over e to the 3x squared. It is, but this is what I was saying about when you have to do the quotient rule for these. What do you notice happens now? This has an e to the 3x. This has a e to the 3x. And now I have 2 on bottom. So I can take the 2 numerators away and cancel 1 with the bottom. Yeah.
Is there like something that you can do to make it clear that that's an exponential?
Well,
Like, can you write something that makes it obvious that it's in the exponent place? Like, if you're writing this in different signs.
You mean like to know it's raised to a power?
Yeah. You like put a line under it or something like to break checks.
I don't think that's a thing.
Oh, okay.
I don't know. I'll look it up. I don't know. It's always wrote it as something smaller. All right, and the last one. You have e to the negative 3 over x. This one's a little bit trickier. Just because it's got like a fraction in there. So again, remember I told you the rule is like e to the u times u prime? If you have something that's a little bit more complicated, do your u off to the side. How could you rewrite negative 3 over x to make it an easier derivative? Because the way it is now, you almost have to do a quotient rule, which is stinky. Like, exactly. What I would do is rewrite it so that the x was brought up as a power of negative 1. So now the derivative of that is just a power rule. So negative 1 times negative 3 is 3. And then the rule is to subtract 1. So you get to the negative 2. So now I feel like once it's pulled away, your derivative is easy because it's e to the u times u prime. So this is the same also as 3 over x squared. So dy dx becomes e to the negative 3 over x times 3 over x squared, which is 3e to the negative 3 over x all over x squared. And if you want to get really tricky with it, this is technically a negative exponent. So it's really 3 over e to the positive 3x times x squared.
It's allowed.
Mm-hmm. Before we do logarithms, do you want to try to do a couple of these like on your own, or do you want to like learn the logs and then do all the practice at the end?
yeah, just do that.
Just keep learning? Yeah. All right. So derivatives of logs. So the rules are very similar because technically a natural log and an e are inverses, right? So just like we did trig, and we started trig with actually finding and proving the derivative ourselves, we're going to do the same thing with a log. We're going to actually find and prove the derivative ourselves. So the question is, find the derivative of y equals ln x using implicit. We'll switch it up. How could I get rid of an ln? How do you get rid of an ln? Literally last night's homework. E both sides. So you e both sides, and you get e to the y equals x. What's the derivative of e to the y? What's the derivative of e to the x? So the derivative of e to the y is times, what do you do if it's dy dx, right? E to the u times du dx. E to the y would be times dy dx. It's the derivative of x. So solve for dy dx.
That was just a rule we're going to learn, and we don't want to have to do it anymore.
Correct. What's y equal to again?
Oh, ln. So it's just 1 over x.
Bada bing, bada boom. Derivative of the natural log of x is 1 over x.
Wait, how did you get the ln x from y?
The original y. So I substituted. Yeah, that's what he's learning right now. Substitution and elimination. It's not like substitution.
No, blame him.
Oh, our turn.
Okay.
And you're going to be substituting in a second.
So the rule of the derivative of ln x is 1 over x. The rule is derivative of ln x is 1 over x. But what if it's the natural log of something other than x? What had happened if it was something other than x for e? What did we have to do? What if it was something other than just x for inverse cosines? What did you have to multiply by? Because it wasn't like meant to be a trick. Like if x is something other than x, you multiply by the derivative of it. So like if it's d dx of ln u, then it's 1 over u times du dx. It's always the u and the u prime. That's how inverse trig was. Inverse cosine of u was u prime over square root 1 minus u squared. Good. Great examples. Differentiate y equals the natural log of x cubed plus 1. What's the u value? What's u prime? So then by rule, dy dx equals 1 over u, which is x cubed plus 1, I have no idea, times u prime, which is 3x squared. So it's really 3x squared over x cubed plus 1. The derivative of ln x cubed plus 1 is 3x squared over x cubed plus 1. Done. Should I do a tangent line for poor Michael? I know. I say it with sincerity. I know you can't tell my sarcasm from my sincereness, but
You don't take it personally.
I know. I know.
We went around the room yesterday and like pretty much everyone said something sarcastic and you didn't pick up on it.
Class was that.
In here yesterday when they were taking their pit test, Cooper, me, Carla, we were all being sarcastic with you.
Yeah.
Oh yeah, it was Wednesday, not yesterday.
Wednesday, my dude.
dudes. Either one of us are dudes. You only have one dude in this room. The rest of us are dudettes.
And I said something and then Cooper said something. And I think some couple of other people.
It's okay. Moving on. Michael, what's the u value of this function?
Sine x.
Perfect. All right, Lex, what's the derivative of sine x? Good. All right, Dom, what's my derivative final answer then with u prime and u?
That would be 1. Oh, would it be then sine over cosine? Cosine over sine.
Yeah.
Oh, yeah, but that's not good. Yeah. Wow.
Yep. So it's really cotan x.
Well, it makes you feel better. I wasn't really sarcastic. I don't understand.
So it's 1 over u times u.
He doesn't use sarcasm. People think he's being sarcastic.
And he's being 100% serious
Yeah.
and mean, yeah. Dom's just a bully, but nobody knows it.
Oh, wait, so,
I'm not a bully. I'm just
well,
I'm
let's
very
not go that far.
straight to the point.
Let's not get there.
I'm very straight to the point. I'm not afraid to tell you if you're wrong or not.
What was the last
Yeah,
one?
they think he's
Uh,
being sarcastic.
Cosine x over sine x, and then that equals cotan x.
Okay, I was gonna say, I thought that was one something.
All right, Miss Anna, this is a chain rule because there is a square root around my inside function.
So do you, when you times it, do you do everything inside? Okay.
So like when we start this problem, it's going to be the derivative of a square root, right? So what's the derivative of a square root? Well, it's 1/2 for the power. Everything inside stays untouched. The ln 2x is not phased yet. We're still just taking the derivative of the square root, which is the power of 1/2 down in front, subtract 1 away. So
Jacob Semino, please report to the office. Jacob Semino to the office.
the derivative of the square root is 1/2, whatever's under the square root, to the negative 1/2. So we've done the outside. Now we have to multiply by the inside's derivative. So the inside derivative is now the derivative of the natural log. So that rule is 1 over u. So that would be like 1 over 2x times the derivative of u. Well, if u is 2x, the derivative of 2x is 2. What do you know about a 2 and a 1/2? Yeah, they cancel each other, so this cancels that. What do you know about a negative exponent? Drops down. So dy dx is really 1 over, you have 2x square root ln 2x. Okay? So it's not, these aren't long, and they're not time consuming. You just have to pay attention to detail. Okay? So now I have the natural log of all of this. This is why yesterday's lesson is so important. What can I do to a natural log that involves division? Yeah, Anna, you mumbled it. I can turn it into what? Yeah. So don't try to do a quotient rule of the inside stuff, because that is going to get gross and messy. Natural logs have really nice derivatives of 1 over u times du dx. And if you think about it, you can kind of hear the quotient rule in that derivative. But manipulate this y so that it becomes the natural log of the top stuff minus the natural log of the bottom stuff. And even still, I should simplify this one more time.
Should that be x plus 1?
Yes. Thank you. A square root is really the same as a 1/2 power, right? But in natural logs, we can do what to our powers? Yeah, bring it out in front as a coefficient. Oh man, that's so much easier. We did it yesterday. All right. Now, I derive these as two separate things. We're going to take the derivative of this, and then we're going to subtract the derivative of that. So ignoring the right stuff, the derivative of ln x plus 1 is 1 over u. So it's 1 over x plus 1 times the derivative of u, or the derivative of x plus 1. Well, the derivative of x is, derivative of 1 is, so the derivative of x plus 1 is, so it really has no effect on it, minus the 1/2 is going to tag along, right? Because it's really like a product rule. So it's like first times the root of the second plus second times the root of the first, but we know the derivative of 1/2 is, I don't want to answer that. Keep going.
I don't know what to do.
Keep going.
I don't take notes, I just watch.
Keep going. Come on, Mom, keep going. Keep going.
Did somebody tell us what to do after that?
Keep going.
Tom, what do you do?
So maybe you didn't. Yeah.
What do you do?
Thank you. You're welcome, Grandma.
All right, so you get 1/2, and then it's 1 over u times the derivative of u, which in this case again is, yep. So then this answer is really 1 over x plus 1 minus 1 over 2x minus 2.
Why is that 2x minus 4?
You could. I just got my parentheses. I didn't distribute.
Sorry, I didn't hear. I heard
Yeah,
you say it and then
yeah. You're good. I know what you thought. You can leave it like that. You don't have to create a common denominator and group like terms on this and that. You're done.
That's nice.
So we've done E. We've done ln. The last one, or what else did we look at yesterday? The very beginning of the lesson, we started with logs. Oh, I think last year I did both the chain rule and the other one. Do you want to see the quotient rule? Like, because I have it on 2 slides. Like, I showed it where I expanded it, and then I showed it where I did the chain rule.
Yeah.
I mean, the quotient rule. We're good?
Yeah.
You just show the work. Ready to leave. Okay, never mind.
Okay? So here's what I want to start with, which is the basic log rule. And then we're going to talk about how you could change this and find this.
Is that last thing like saying you, Brian?
Yes.
Okay.
Yesterday, we talked about how you could transform log base a of u equals y, or instead of a u, it was just an x, into another formula. So do we remember what the other formula was? This becomes the same thing as not a to the u.
Because the y equals u.
Yep. What do you notice about the end of the logarithm formula over there? What's it look like? What's the end of this derivative look like?
The other one that we just did.
The ln. Yeah. Does anybody remember the change of base formula for a log? So, do you remember if you wanted to solve for these, but like a to the y wasn't like a nice number, then you could use what they called the change of base. So change of base says the log of a to the u is the same as the natural log of u over the natural log of a.
How do you remember that?
Isn't that how you like
Do it on a calculator.
Yeah.
Because your calculators in the past weren't smart enough, but now the calculators actually have this on them. But in the past, you had to do this to do it on the calculator. What do we know about ln of a? It's really just like a number. So, isn't this kind of just a product rule? 1 over ln a is like a number. So it's the first times derivative of the second. We just said derivative of ln u is plus the second times derivative of the first, but the derivative of a number is that. Is how this becomes that. That is where this derivative came from. Change of base, taking its derivative. And that's kind of like what I show here. So this becomes change of base. If you derived it, you end up with this derivative here because change of base creates ln u and natural log of a. So if you get stuck and you forget the log derivative, you can change of base it and take the derivative of a natural log, which you definitely will never forget because we do too many of them. And again, the idea is that this is plus 0 because the natural log of a is just a number. I like to know where things come from. It helps me see it. Can't tell if that was a hiccup or a burp. What's this thing?
I'm not really a pleasant person. As far as human interaction. Carlos, how the heck did you know that?
It was in yesterday's notes, by the way. All right. Let's do some examples. Are you still copying down and use the change of base stuff? Okay. Yeah, I kind of have to.
Oh my goodness.
Don't worry about it. Okay. Log base 10 of 2 plus sine x. So this is like my u. What's the derivative of 2? It's derivative of sine So then the derivative of this problem is 1 over ln a, where a is the base of the log. So it's 1 over ln 10 times 1 over u, which is the inside of the log, times the derivative of the log inside, which is cosine. That's fantastic. So cleaning it up, you just get cosine x times ln 10, 2 plus sine x. Nothing cancels, nothing simplifies, it doesn't become pretty.
ln 10 doesn't have like a nice number.
I don't think so.
Okay, cool.
Most ln's aren't nice numbers. The only ln that's a nice number is the ln of 1.
Which is 0.
Correct.
But the ln of 0.
Is undefined. Okay, so the log kind of hits at a to the u in a way too. So we sometimes need to take the derivative of a number to a function. So this is a manipulation of e in a way. So e to the u is equal to e to the u times u prime. The only thing that's being added in is this ln of a. The reason you don't see the ln of a with the e to the u, so go back to this idea, right? If you applied this rule to e to the u, you'd get e to the u times ln e times u prime. But what do you know about ln e? It's 1. So technically this is the e to the u rule. It's just that the ln of e cancels. So 10 to the 2x. This is the one that like everybody I kind of feel like has the hardest time remembering how to do. It's like the E problems, right? You literally rewrite the problem. You take the derivative of the power. So derivative of 2x is the only thing you have to add is the natural log of the base. Not pretty, it doesn't simplify, it doesn't clean up. It is what it is. What could, yeah.
Is it possible? I don't know if it's possible. Is it possible to make that into a log and then find it that way, or is that like impossible?
You want to turn this back to a log?
Yeah. Like just
so
in case, like if you forgot the formula or something.
it would be like log base 10 of y equals
2x.
and then you'd have to do 1 over ln 10 times 1 over u times dy dx.
How many times you gonna ask this, Jimmy? He's asked me 4 times where I am 7th and 8th period. I don't know if you can't remember or not. Jimmy Sadler, yes.
Equals
No,
2.
you're trying to text me through Instagram.
So then you get dy dx, probably in my class, equals 2
Yeah.
times 1 over ln 10 times 1 over y.
No, it wouldn't be times the fraction, it'd be times. Why did it just be 2?
Oh, it would be I was adding them. These would actually both come up to your numerator because you'd be multiplying by the reciprocal.
Yeah, so you get the same thing.
You do. You do. So it works.
Okay,
Sorry.
thank you.
I'd be dividing by my fractions.
Stay on your toner as well.
Also, I said sometimes I have trouble like doing math on the board that I haven't done by hand before because I have like trouble stepping back and seeing.
Yeah.
All right.
Begin with.
Now it's page 178. If you want to see what I did, I actually did the evens. I know the evens aren't in your book, so if you're going to want my work, oh, that's a big deal.
Yes, you may.
I don't care if you choose to do the evens or the odds for
Are you
them.
doing evens or odds for 1 through 10 too, or 1 through 10 all?
I guess you're doing 1 through 10. Actually, you're doing 1 to 16 all.
Okay.
And then 17 to 27 odd. Because I had to add back to this, just for this case, the exponentials to catch up for that day.
Now we're playing mustard.